Hello once again, folks. Welcome back to the Geodynamics video lectures on the basics of fluid mechanics. Here in the final lecture on this topic, we will talk about pipe flow. And we'll do that by basically calculating the velocity field of a fluid flowing through a pipe, and we'll describe along the way what a pipe looks like and things like that, balance the forces, just like we've done previously for 1D channel flows. Then at the end, we'll talk about the Reynolds number, what it means, and why it is a useful number. As I mentioned before, pipe flow is something that can be used, for instance, to calculate the flow of magma as it's rising through the neck of a volcano. So we could look at the flow of a material like that within a pipe-shaped volcano neck. There are also other geological applications as well. Now, in contrast to what we've seen for 1D channel flows, there we were looking at a confined channel that was of infinite width, and here we're looking at a fluid flowing through a round pipe. And so you can see here a cross section through the pipe, and the pipe has a radius that is labeled at capital R. Now, as you can imagine, for a solid piece of pipe, we're not going to be looking at any fluid flow that's the result of the sides of the pipe moving, but it's really only going to be driven by a pressure difference along the length of the pipe. So here we have then a cross section, a slice through the pipe along its length, and you can see in this case the length of this piece of pipe is L. There's a pressure difference on one end, P1, on the other end, P0, and along that length L, we then have a drop in pressure. And we're assuming that the velocity within this pipe is then only going to vary as a function of the distance lowercase r, where lowercase r is the distance from the center of the pipe to whatever position within the pipe. So for a given portion of the pipe with a radius lowercase r, the pressure force on the ends here and here will be balanced by a shear force that's acting within the fluid, here labeled as tau, and you can see it's acting in the opposite direction of the flow of the fluid in the pipe. So we can then set our pressure force as a result of the change in pressure equal to the shear force, and then balance the forces that are acting on this fluid. So our pressure force is simply the change in pressure, P1 minus P0, times pi r squared, that's the area of the little piece that we're looking at, and that's equal to a shear force, which is simply minus 2 pi r L and tau. And in this case, the tau, again, is acting in the direction opposite of the flow of the fluid in the pipe. And if we recognize this P1 minus P0 term from before, we can do a little bit of math. We can drop out our pi's, rearrange things a little bit, and simplify this relationship to say that tau is equal to r over 2 times dp dx, where dp dx is the pressure gradient mentioned in the previous lectures on channel flow. Now for a Newtonian fluid in a cylinder, remember we're flowing down the pipe, and so a little piece in the middle of it would be a cylinder shape. The flow law, or the constitutive relationship that we would have for this Newtonian fluid would be saying that the shear stress tau is equal to eta times du dr. So previously we had something like du dy. Now we're just talking about du dr. It's the distance from the center, that little radius dr in this case. And we can then plug this thing into the equation we saw on the previous slide, our force balance equation, and that will give us a relationship for the slope of the velocity, and this would be then du dr, as being equal to r over 2 eta times the pressure gradient dp dx. So now we have something that is capable of being integrated to give us a velocity in terms of pressure and the pressure gradient dp dx. So if we integrate that one time, it's not terribly difficult. And we can find that our velocity u is equal to minus 1 over 4 eta times the pressure gradient dP dx times big R squared minus little r squared. So that's our distance from the center of the pipe again. Now, if you look at this equation and based on it, what would you say is the maximum flow velocity in the pipe? And this is something you can calculate, and you don't need to plug in numbers or anything like that. I just want you to try and calculate this symbolically. So go ahead and pause the video and see what you calculate for the maximum flow velocity in the middle of this pipe. Okay, so you might have heard that I gave you a little bit of a clue in saying that the flow velocity is going to be the maximum in the middle. You probably could already see that from this picture here of the velocity field within this pipe. And all you have to do here is plug in little r equals 0 to the equation we had on the previous slide, because that's where the maximum velocity is going to occur. And you simply get big R squared over, or sorry, minus big R squared over 4 eta times the pressure gradient dP dx. Okay, so the last thing I want to talk about here about pipe flow, we've calculated the velocity field now, and everything will work just fine with our velocity calculation, provided the fluid flowing in the pipe is flowing in a laminar fashion and it's not turbulent. So what does that mean? Well, laminar flow means that the fluid is flowing in parallel flow lines. So all the velocity vectors within this fluid are all parallel to one another. In turbulent flow, you start to develop eddies and little currents and small-scale circulation within the pipe. And obviously, our velocity equation is not intended for that case. How do you know which one of these scenarios you're dealing with? Well, you can actually make that determination using something called the Reynolds number. And it's a dimensionless parameter that you can simply calculate for a fluid if you know a few things about it. So here's the equation for the Reynolds number. It's simply rho times u bar times d divided by eta, where rho is the fluid density, u bar is the mean flow velocity, the average flow velocity within the pipe, and d is the pipe diameter, simply 2 times the radius big R. Eta, of course, is our viscosity from before. And what we know is that for a Reynolds number of greater than approximately 2200, we transition from laminar flow to turbulent flow. So if you plug in your fluid properties, the average flow velocity, etc., what you will find is that if your Reynolds number is less than approximately 2200, it should be laminar flow, and if it's greater than that, then it's turbulent, and our equation for the velocity will not work as expected. Okay, so that was our last topic on fluid mechanics, a little bit about pipe flow. Go ahead and take your quiz, and then we'll see you for the next video lecture set.